Look at this problem trying to figure out electric fields. So a field, electric field, is kind of a map of our space showing where the strength, how strong the force would be for a hypothetical charge. So electric field is force divided by charge. So unit-wise, it's newtons per coulomb. Or if we rearrange this, the force, if we wanted to know what the force is, we just take the charge times the electric field. And so if we know the electric field, in general, anywhere we are in this, say the plane of the paper, they say here at point A, if we know what we want to put a charge of something here, 1 nanocoulomb, then if we knew the field, we just multiply the field times 1, and we have our force, or 1 times 10 to the negative 9. Same thing for B. We could, if we knew the field here at point B, we could just take that our charge times that field, and we would get our force. And so it's a map. We can get our force for any general charge that we might have. So it's kind of a general map, force per charge. All right, so we call it an electric field. It is a vector. It has direction. You should have seen in the theory kind of things, electric fields come, so we've called this a plus 2 nanocoulomb. This is -4. Field lines come out of positives and go into negatives. So the field lines would be going like this, going around here, into there. I'm not drawing them to scale very well, but they come out of positives and into negatives, and they're symmetrically spaced around here. And then, but since this charge is twice the size of this charge, this one will have twice as many lines coming in. The field is going to be stronger inside there. And the formula for the field around point charges like this, we have field is force over charge, and force, so force over charge. And we're thinking of the charge here, the divided by charge is like a test charge. Any sample, a little pot, think of putting a little plus, a little tiny plus charge at certain different spots, and we're going to see what kind of force it feels, and then divide out the charge, and so that we can get a generic field strength. So, but what was the force? What did Coulomb tell us? The force is Q over R squared, R hat, and then we're going to divide that by Q. So these Q of the test charge will cancel out, right, because it was in the force equation, but then we're dividing by it again, so it's gone. So E for a point charge then is just KQ R hat over R squared. What are these R's? R is the distance from the charge, right? And Q is the coulombs. This R hat, though, is the direction vector, right? And so the direction of the force is the same as the direction of the field, right? Remember, we calculated that last time we were talking about Coulomb's law, so it has to do with it's on a line directly in between, and the direction depends on the attraction depends on whether it's positive or negative, or whether they're alike or unlike charges, right? Okay, so for a point charge, E is KQ R hat over R squared. And yeah, that's how it gets to be newtons per coulomb. We're going to, again, do the superposition idea. So looking at our little picture here, if we're trying to find EB, and so on this, for charge 1, R1 is R1B, I guess, is on this line. This is a positive charge, and this is a positive charge. It's going to be trying to push it away, right? So it's going to be something like this. It'll be EB from 1, right? How about what is 2 going to do to it? 2 is a negative charge, right? And again, the line of action is in between the 2 points. So is it going to be pulling or pushing? It's going to be pulling it towards it. 2 is twice as big and is quite a bit closer, so 2 is going to be having a bigger field, bigger force, bigger field. So EB2 might be something like that. Hopefully you can see that all right. And so the total would be those two added together. Kind of draw a parallelogram here. The total should be something along those lines. Excuse me, EB should be something like that. And it's not too bad. So in general, if we're trying to find the field at any certain point, the field lines, we should just do it, at this point it should be tangent. So the field itself is a tangent line at any point on here. So these lines, think of it joining all the little bitty electric field arrows for all different points. So this, on this line that I kind of drew here, that's kind of tangent to it. Not too bad. Maybe not too bad. All right, but we're not doing this graphically. We're actually trying to calculate numbers. So let's get some numbers here. So we got our figure, we got our data on there pretty well. We're just going to count. This one is at 6, 0. This one is at 3, 0, or negative 3, 0. This one's at 3, 4. We got our sizes. Okay, so now let's go ahead and calculate the pieces of the field. So EB1, magnitude-wise, let's calculate the magnitudes first, and then we'll calculate the angles. So EB1 is KQ1 over RB1 squared, right, size-wise, which K is still 8.9876, 10 to the 9th, Newton meters squared per Coulomb squared. Run out of room. Q1 is 2 times 10 to the negative 9 coulombs. What is RB1? RB1, we're going to have something, it's going to be meters, and then we're going to square it. So it's checking our units. Meter squared cancels. One of the coulombs cancels. We end up with newtons per coulomb, which is what we're supposed to get, so that's good. All right, back to what is RB1. RB1 is this. All right, so we got 6 over and 4 up. So it's going to be RB1 squared. So RB1 squared is 6 squared, 6 centimeters squared plus 4 centimeters squared, right? Right? A squared plus B squared equals C squared. So RB1 squared is 0.06 squared plus 0.04 squared. No, we already took care of the squared in this. Okay. So EB1, magnitude-wise, 8.9876 E9 times 2E negative 9 divided by, in parentheses, 0.06 squared plus 0.04 squared. 3.4567, okay, 3.457 should be plenty, times 10 to the 3rd newtons per coulomb. All right, which is kilonewtons per coulomb. All right, that's the magnitude of EB1. Let's get the magnitude of EB2. Very similar. KQ2 over RB2 squared. K 8.9876. 10 to the 9th. Q2, 4 times 10 to the negative 9. Again, we're just doing magnitudes. Don't worry about the negative sign for now. We'll get that when we do our vector directions. What is RB2 squared? So again, we got triangle here. This side is 3, this side is 4. So C is the square root of A squared plus B squared, square root of 0.03 squared plus 0.04 squared. And that's going to be meters since we put everything in the right units. So EB2 magnitude is 8.9876 E9 times 4E negative 9 divided by, in parentheses, 0.03 squared plus 0.04 squared. Something's gone bad here. .03, .04, okay. 14.38. So do that one about 3, this one's about 14, maybe not quite 5 times like it should be, but not too horrible. 10 to the 3rd newtons per coulomb. So my picture will be a little off, but hopefully we'll get the idea. All right, so this is a magnitude, but we can't just add those together or you'll get it wrong because they're not going the same direction, right? And so we need to get their directions. That'll be a bit of a pain. Okay, so EB1 is going off this way, We need its angle with respect to the horizontal, so we can do cosine and sine kind of stuff, right? And so that's the same angle here, this theta 1, right? And so we can say that tangent of theta 1, alright, tangent of theta 1, why do I keep writing prime? Theta 1, tangent is opposite over adjacent, opposite over adjacent. Opposite is 4, adjacent is 1, 2, 3, 1, 2, 3, 6. So theta 1 is tan inverse of 4 over 6. Tan inverse 4 divided by 6. 33.69 degrees. Alright, so we can use that to get EB1 as a vector. EB1 as a vector is going to be EB1 magnitude cosine theta 1 plus times I hat plus EB1 sine theta 1 j hat. So let's just check. Is it j hat? Yes, because it's going, x is positive I hat, y is positive j hat. So those are both good. All right, and so EB1 3.457. We'll just do things in kilonewtons. Cosine of 33.69 plus 3.457 sine 33.69. So EB1 3.457. What is going on? 3.457 times cosine of 33.69. 2.876 I hat plus 3.457 sine of 33.69, 1.918 j hat kilonewtons per coulomb. All right, EB1. EB2, same kind of general formula. EB2 magnitude cosine theta 2 I hat. Well, let's just check. Is it I hat or is it negative I hat? EB2. So EB2 is here, going this way. X direction is positive I hat, but EB2 sine theta 2, the y component is going down, so it's going to get multiplied by a negative j hat kilonewtons per coulomb. Okay, what are the sizes of these? We need to get theta. We need we're going to break this into pieces. I don't know if we can see this. What color? Just typing. So we're going to have the x component here and the y component here. All right, this is going to be EB2x, which is EB2 cosine theta 2, whereas this one is EB2y, EB2 sine theta 2, where this is theta 2 in here. All right, so how can we figure out theta 2? Just kind of like we did with this. Tangent of theta 2 is what? Tangent of theta 2 is opposite over adjacent, which is, in terms of the distances, right? Similar triangles for the forces and the distances. These are force pictures, but we can look at the distance pictures. And so opposite is 4, and adjacent is just this much, which is 3. And so theta 2 is tan inverse of 4 over 3. Tan inverse 4 divided by 3. 53.13. So EB2, using this formula here, EB2 magnitude 14.38, we'll do it in kilonewtons, cosine of 53.13, I hat minus, with a minus j, 14.38, sine 53.13, j hat, kilonewtons per coulomb. EB2 as a vector then is 14.38 times cosine 53.13, 8.628, I hat minus 8.38 sine of 53.13, 11.50, j hat, kilonewtons per coulomb. Okay, so we were looking for E total, which is those two added together. So we got both E's as vectors. So EB, the whole EB, is EB1 as a vector plus EB2 as a vector. EB1 as a vector, 2.876 I hat plus 1.981, 918 I mean, j hat plus EB2, 8.628 I hat minus 11.50. Again, gotta add only i's to i's, j's to j's, can't mix them together, it'll be wrong. So 2.876 plus 8.628. Those are the two I parts. 11.50. Interesting. I hat, and then the j's 1.918 minus 11.50. So the minuses win, so it's minus 9.58 j hat. Let me just double check there. Okay. I don't know why 11.5s just showed up, but it looks okay. Okay. And this is still kilonewtons per coulomb. All right, so 11 in the I, so it's almost, you know, 11 and 10 is not too far from a 45-degree angle, but it's going down for the total. You know, I don't know. It's a little bit less than a 45 degrees going down. It's supposed to be going down 9.5 and over 11.5, down 11.5 over. So not too bad. So this is our EB that we're talking about in here. The total EB for the two pieces added together. A tangent to that curve like we tried, to that field line that we tried to show. Okay. Well, so there you have it. So kind of like the forces, got to get the components, keep them as vectors, add them together. But now say we wanted to find, you know, what is the force if I put a 10 nanocoulomb or a 1 microcoulomb charge right there. How would I know what its force is? All I have to do is take 1 microcoulomb times this number. Microcoulomb is just a scalar, so just a scalar. 10 times 10, or 1 microcoulomb, 1 times 10 to the negative 6 times this, and then I've got the force at that spot. Or if I wanted 2 microcoulomb, just multiply that by 2 times 10 to the negative 6. So it's easy to just find the force on any charge we want to once we have the field calculated. So there we have it.